we will discuss the energy and the hydraulic grade lines. Okay, hydraulic grade line is also called as a hydraulic gradient. It is the graphical representation of the total potential energy of flow, or the sum of the elevation head and the pressure head, or Z plus P over gamma. And they are measured from the reference datum. It is also the line that connects the water levels in the successive piezometer tubes placed at the intervals along the pipe. And this water level is called the piezometric head. If this is the pipe, okay, if this is the pipe from the reference datum, and it contains liquid flowing in this direction, having a flow rate of Q. Try to imagine what will happen if you are going to make a hole and you place a tube. Okay. So, the water, when there is a hole, it will rise inside the tube and until or it will stop until it reach its static head. Okay, and this will be now the water surface. This tube is our piezometer, which is a measuring device used to measure the pressure head of the liquid from the reference datum. If this is your section 1 and this is your section 2, okay, this is your section 2. So the pressure head here will be P1 and this one will be P2 over gamma. If we try to connect the water level, the line now is called the hydraulic grade line or hydraulic gradient. This column rise of, or the rise of the column of water is also called the pressure head. So what are the characteristics of the hydraulic grade line? First, hydraulic grade line slopes downward in the direction of flow, but it may rise or fall due to changes in velocity or pressure. Okay, if there is changes in velocity or pressure, the hydraulic grade line will rise or fall. Second, for uniform pipe cross-section, the hydraulic grade line is parallel to the energy grade line. Third characteristic is for horizontal pipes with uniform pipe diameter, the drop in pressure head between any points is also equal to the head loss between these points. So, from the figure, it is said that the drop, okay, the drop of the pressure between any points or between section 1 and section 2, okay, so this is the pressure at section 1 and this will be the pressure at section 2. So the difference between the pressure is also called head loss. Okay, I hope you remember those characteristics. Next is the total energy grade line. What is this? This is a graphical representation to the total energy of flow, or the sum of the kinetic and the potential energy. So what are the kinetic energy? Those are the velocity head, and the potential energy are due to the pressure and the elevation of the fluid. Okay? The elevation head. So we have now total head is equal to the pressure head plus elevation head plus the velocity head. When the fluid flows along the pipe, there is loss of head, and the total energy decreases in the direction of flow. If the total energy at various points along the axis of the pipe is plotted and joined by the line, okay, this line is called the total energy grade line, the total energy line, or the energy line. So, what are the characteristic of this energy grade line? So, energy grade line always loop downward in the direction of flow. So, the same of the hydraulic grade line. And it will only rise with the presence of the pump. So, the energy grade line will change. It will rise if there is a presence of the pump, and it will drop. Okay, it will drop if there is a presence of turbine. Okay, there is a rise if there is pump, and it will drop if there is a presence of that turbine. The drop of energy grade line between 2 points is also called as the head loss of these 2 points. Then, if the pipe has a uniform diameter or cross section, so the energy grade line is also parallel to the hydraulic grade line. And the energy grade line is always above the hydraulic grade line, but the amount equal to the velocity, okay, by the amount equal to the velocity head. So the difference between the energy grade line and the hydraulic grade line is equal to the velocity head. Okay, if we neglect the head loss, energy grade line is horizontal. If we are going to look at this figure, okay, this is from the reservoir, and we let this one as, okay, we let that one as A, and this will be your reservoir B. This will be the intake of the pipe from the reservoir, and this is the, okay, this is the discharge point. So here, the pipe from the reservoir A, okay, there is a, we let this one pipe 1, and this is a pipe 2 and pipe 3. So as you can see, pipe 1, there is a sudden contraction, okay, because pipe 2, the diameter of the pipe 2 is lesser than the diameter of the pipe 1. Then the diameter of pipe 3 is greater than the diameter of pipe 2. So there is a sudden expansion of the pipe from pipe 2 to pipe 3. Okay. So it is said, for what is the characteristic? So since there's no pump, or there's no presence of pump here, so the total energy grade line is, there is a fall of the total energy grade line due to the minor losses. So what are these minor losses? That is the loss from the entrance of the pipe, then the sudden expansion of the pipe, and the sudden contraction of the pipe. So here, the total energy at reservoir A is from here. Okay, since there is a loss at the entrance, so let's say this will be now the, if we are trying to connect no the total energy at reservoir A and the entrance, so there is a drop of energy. Then for pipe 1, there is a loss. And what are these losses? Also the friction loss. So the at here for pipe 1, we just write like this. There is also a loss. So we have the total energy at this point minus the head loss due to the pipe friction. So this will be now um, the total head. Okay, minus the sudden contraction. So there is also a loss. Then there is also a loss of the pipe 2, and there is also a loss for the sudden expansion of the pipe. Then there is also a loss at the discharge point. So if the end of the pipe or if the pipe discharges to another reservoir, so there is a loss. But if the pipe discharges freely into the air, so there's no head loss due to the discharge. So from here, since the pipe discharges water from reservoir A to reservoir B, so there is a head loss at the discharge. So here, we will try to draw. So at this point, no, if minus, so there, this is the head at this point. So minus the head loss at the, okay, the head loss at the uh, discharge. So it can be like this, that the head loss or the total energy at this point will be equal to the elevation of reservoir B. Okay? So the difference, okay, this will be your energy grade line. The difference of the energy grade line and hydraulic grade line is separated by the, okay, is separated by the, okay, the difference, if this is your, it will follow, no, the hydraulic grade line. It will follow because the difference is just equal to the velocity head of pipe 1, and here this is the velocity head of pipe 2, and here this is, okay, and here this is just the difference between the velocity head of pipe 3. Okay, so I hope you understand okay, I hope you understand this. And if I'm trying to let you sketch the energy grade line and the hydraulic grade line of a certain problem, you can uh, you can get the, or you can sketch the energy grade line and hydraulic grade line. Okay,